Yeah, it's a core ticket. Let me look it up. I'll elaborate in a minute.
Okay.
It's not urgent.
Yeah. We kind of have a full plate today, I think, depending on how much Daniel has to present us. He's going to try to get us up to speed with some category theory stuff.
Um,
So uh,
Fair
yeah,
enough.
but maybe next week. I definitely want to. That sounds interesting. So um, so yeah, please pull up that ticket. Okay, so I thought I would just give a quick review since last week we mostly talked about bisimulation, or on Monday we mostly talked about bisimulation in Greg's lecture, and we already discussed bisimulation a little bit, but Greg also introduced somewhat another process relationship that in the PyCalculus paper is called congruence, that is sort of dependent on this notion of context. So I thought I'd give a quick review of that, and then we can hop into some category theory stuff, introduction to linear theories with Daniel. Um, so from a high level, when we're thinking about process calculi, we want different ways to compare certain processes. So we went over structural equivalence, which is ways that we can compare processes that are sort of written down on a piece of paper, and it's really just sort of a minimal way of comparing processes where we're just abstracting away parts of our syntax that we weren't intending to exist. And then we have bisimulation, which gives us a little bit different of a notion of when two processes are equivalent. And this is that given it allows you to specify a portion of the process that you care about. So in our example of n-bar bisimulation on the PyCalculus that we talked about 2 weeks ago, our observation relationship were just the outputs on some subset of names that we defined that set of. So that gave us a way to say, okay, we have a process and we really only care about these portions, these outputs of a process. These are the things that we're interacting with and observing. But another process could maybe have the same behavior over here in this set, but maybe be sending and receiving on other names in order to simulate that behavior. And so if these two processes can sort of have this same effect over here, which this effect is defined on our barbs, then we call those two processes bisimulations of each other. But then there's this stronger idea yet of reduction congruence, which is that given I have this little package of a process and I push that into some context, and I have two of these, are they going to behave the same? So I have a quick example here where when we had the process X output something, Z output something, and we were observing on the set of names X and Y, we would call that whole top process there as n-barbed similar to X output Y. Do we remember that? Does that, any questions there? Okay, so then we can see that these two processes are not reduction congruent though, because if you consider the context where we have a hole here and then we run whatever is dropped into that hole in parallel with an input on Z, and then we output something on Y. So we can see that in this top process here, if we drop it into this hole, so this is our whole process construction here, it reduces to a send on X and a send on Y, which means that we're observable at both at X and Y. But if we drop just this process here into the hole, we get this process down here. And we can see that this process is never observable at Y because there's this, nothing is ever sent to Z. So that is sort of the difference between reduction congruences and barbed bisimilarity. And the reduction congruence, I guess things get a little interesting there, because now you have this infinite set of contexts from which you have to sort of compare against to see if two things are congruent, if two processes are congruent or not. So there is a notion of, you bring in this idea of labeled transitions, and you can use those to define some sort of minimal set of contexts from which you would need to compare two processes to say that they're similar. And that, I linked a paper in the invite to this that I think goes over that some, but I haven't had a chance to review that or understand that portion of things. So what questions do you have about that material? Or is there anything that was a little bit unclear that you'd like me to review there?
I have a question about Bisimulation. When we put a hole on the output, but can we put the hole on the input process? Does this make sense?
So by simulation, we're not really worrying about holes yet.
Okay, but my question is really about the hole. Yeah.
Okay, so the holes, where can we put those holes is what you're asking.
Yeah, yeah.
Okay,
when we have like a bar with input and output, we have a hole on the output side. Can we have a hole on the input side?
Yeah, I mean, so we can have a hole wherever we could put a process normally. So yeah, the way that we defined our holes was by our type derivative, and what that gave us is that, yeah, anywhere where a normal process could be, we could define that as a hole. Now with our construction for our holes, we've only been talking about one hole context, meaning that in your whole process, there's only ever going to be one hole somewhere. But I mean, I think theoretically then, right, our hole could be inside of a name, right? Because processes are just quoted names. So our hole could be there.
Oh, okay. Thanks.
Yeah. What other questions? All right. Daniel, yeah, I invite you to take it away now then.
Okay, sounds good. So I prepared some slides, so I'll just share my screen here. Let me see. Here we go. Okay. Did that work? Can everyone see the slide?
Yeah.
Okay.
Yeah.
So I'm going to try to make this as unmathematical as possible, which isn't the easiest thing to do since I've only thought about these in a mathematical context. But let's see what we can do. So there's really a lot to Leverrier theory. So today I figure we could just really try to break down what the definition is and not even really go into an example or go into the relationship with monads, because I don't know, in one sitting, that's kind of a lot to deal with. So why does this, like, where did Leverrier theories even come from? Well, really, this is a way to study algebraic structure. So if you were to take like an upper division undergraduate math course in abstract algebra, you'd start to learn about all these different mathematical algebraic gadgets, which are basically just ways of combining different operations, like things like you can multiply, places where you can add or sometimes subtract. So these are kind of different things on that menu. And how do I, sorry, I want to put this in a presentation mode. But there we go. And so typically like an algebraist, they might study an instance of one of those algebraic structures. But a universal algebraist will actually want to study the structure itself. And so instead of studying a particular group, they want to study groups, the notion of groups. Or instead of wanting to study like a particular vector space, they want to study vector spaces as a vector space. And so there's this topic called universal algebra, and Levier theories were created by Bill Levier in his PhD thesis, really to take this study of universal algebra and put it into the language of category theory. And he vastly generalized things along the way. Okay, so I guess we'll just start with the quote unquote real definition of a Levier theory, which is pretty intense. So there's this, we start with a small category, and if it has finite products together with a strict finite product preserving identity on objects functor, where this left null denotes a skeleton of the category finite sense, we call this thing a Levier theory. So I emphasize some of those words and phrases because those in and of themselves are probably difficult concepts. So we're defining a difficult thing on top of already difficult things. Fortunately, there's a nice working definition that simplifies things substantially. So we can instead deal with this definition as opposed to the real quote unquote definition. So really what we can think of a Levier theory as is just a category with finite products where every object inside this category is of the form m times m times m, so on for some finitely many times for some single generating object m. So today, I guess we can just sort of try to understand what this definition means. So I think we all have very different backgrounds when it comes to category theory, so I'm not going to assume really anything. So we'll start with the first possibly unknown term in this definition, just the word category. And again, it's going to be a very loose and pragmatic approach to trying to teach this stuff. I'm not going to try to be very rigorous at all. So first thing we got to do is understand what a category is. So very loosely, a category consists of a number of things. First of all, a collection of things we call objects. So we usually denote them with lowercase letters, sometimes uppercase letters, but you could it's a collection of things called objects or primitive notions. And there's also a collection of things called arrows. And these arrows go between objects. So there's no such thing as an arrow without a pair of objects associated to it. So there's two objects. Those objects need not be distinct, but we're always going from an object to an object. And this is another primitive notion.
Can I interrupt real quick with a question?
Absolutely, yeah.
So the category, it has to have both the collection of objects and the collection of arrows, is that right? Because
Yeah.
I'm trying to think about what makes it different from just like a set of these objects, X, Y, Z.
Well, it's definitely closely related, but you can kind of think of it as adding an extra dimension in a sense.
Okay.
So if you just think of a set as a collection of dots, like a bag of dots, that's all a set is, right? It's just a bag of dots. Well, what a category adds to this bag of dots is a way of going between dots.
And that's the arrows, right?
Those are the arrows, yeah.
Okay, cool. Thank you very much.
Mm-hmm. So you can almost think of arrows as processes if you want. It's not completely accurate, but it's not, I don't think it's a dangerous sort of thing to keep in the back of your mind as you're trying to learn this stuff. So if that's like a comfortable thing, then I definitely suggest that.
Yeah, cool. Thanks a lot.
Okay, so there, it's not only this collection of objects and this collection of arrows, though. There also has to be a way to compose arrows. So that is, given any two arrows, if one stops where the other one begins, then we automatically get a new arrow, which we call the composite arrow. That composite arrow, there's several notations for it. I think the more computer sciencey notation uses this, uses this semicolon, and we read it from left to right, so that F is the arrow that goes first, and G is the arrow that goes right. This is different than the order that you would see if you were to come across notation in like a calculus class.
Who's Thomas?
They're usually flipped. Okay, so this means, this is something that we have to be able to do with the arrows, right? So for any two so-called composable arrows, you have to be able to compose them. And they're only composable if they pick up and start at the same place.
So if those were functions, that would really be g of f of x.
Exactly, yeah. That's exactly what it is, yeah. Okay, and then another thing that we need is for every object, we associate an identity arrow. So the identity arrow is basically an arrow that does nothing, if you're thinking of it in processes. And in a sense, it does nothing is this equation that I have down here, that if we take this arrow from x to y, and it's f followed by the identity on y, that's the same thing as just doing f, because the identity on y does nothing once we get to y. Similarly, we can also do nothing to begin with. So we can start at x, do nothing, and then do f. And that's the same. So having these identities here is actually something that's really powerful in terms of evaluating whether objects are the same. And I sort of put a weird inflection on the word same because category theory has a lot of different gradations of what it means to be the same, which I'm not going to get into, and it's not going to be apparent how having these identity arrows can do that. But just, it's, I guess just so you can have in the back of your minds that these identity arrows, they seem like they do nothing, but they actually, having them there does a lot. Mostly to be able to compare things with, rather than to be able to do things with.
So I'm seeing another notion that like our arrows are labeled, and that we can talk about those so you can tell if you're like taking an arrow, if it's an identity arrow versus a different one. Is that like a base concept as well, or?
Yes, so you can always say, oh, I'm gonna pick out the identity arrow and use that one explicitly. Like there's a deterministic process of picking out an arrow that you want to work with.
Okay.
But it depends on how you get at the arrows too, because you may be in the midst of some long proof where these arrows sort of present themselves to you by way of, I don't know, just whatever you're doing, and in the context in which you're working, you may just come across a series of arrows, and you may not know what they are, but your job would be to try to figure out what they are, at least relative to other arrows that you do know what they are.
So you just mentioned for a second, you just mentioned the phrase "the identity arrow." Is that correct? Is there like an identity arrow, or is it more like for each object there's one identity arrow?
Oh, okay, that's a good question. So for each object, there's a unique identity arrow.
Okay, cool.
Now, that's not part of the definition, but that does follow from the axioms.
Okay, cool.
Like you can prove that.
So is there, like, if I have a set of all my objects, like you used X, Y, Z as example, are we guaranteed anything about like what arrows exist or don't exist? Is there definitely one from X to Y and X to Z and Z to X, or how's that work?
No, the only thing that's guaranteed are the identity arrows.
Okay, cool.
So really, all right, so something that's kind of fun but frustrating about category theory is that it subsumes just so many concepts. And in fact, so many things actually are categories that you wouldn't naturally think are categories. Like for instance, just a set itself can be thought of as a category. So if I just have a set of 3 elements, A, B, C, then I can think of that as a category whose objects are A, B, C, and whose arrows are only the identity arrows and contain no other arrows. So really set theory in a very real sense is subsumed by category theory in this way. So yes, are there any other questions at this point? Okay, so there's more to the definition. There's other axioms, but they're not terribly important to be able to work with category. So I'm just gonna stick with these, which I'll just call the big 4 things for now, right? So you have to have objects, you have arrows, you can compose arrows, and you have identity arrows. So these are like the most important things to take away.
This Kayvon, I have a question. What is your reasoning for calling them arrows rather than functions?
Well, functions is very is particular to sets. So a function is like a thing that goes between sets and takes as an input an element of the set and gives an associated output. Well, here the thing about the objects here, we're not allowed to look inside these things. So there are no elements inside of these objects. So we can't really talk about it eating an input and spitting out an output. We're sort of taking a macro view as opposed to a micro view here. And we're taking a very behavioral view as opposed to like an internal clockwork view. So if these objects were little humans running around the world and I was a psychologist trying to understand them, I would study them by learning about how they interact with other people via these arrows, as opposed to via like me trying to sit them down on a couch and do some Freudian analysis or something like that on them. So arrows is used because it's a more general concept than function, I guess. Or function has a sort of, what's the term? I can't think of the word right now I'm trying to think of, but there's a function, I guess, is too specific for what we want. But another popular term is morphism. That's another common one that you might have heard of. Does that help answer your question?
I think it's just a definition thing, but I get the gist of what you're saying. Thank you.
Okay. So I guess what I can say is that the sort of archetypal category has as its objects all the sets, and as its arrows all the functions between sets. So in that sense, an arrow can be a function in particular instances of categories. But it need not be a function like that, right? Because so maybe that's helpful too. Okay, so I guess there's the definition of a category. So let's get back to this definition. So Leverrier theory is a category, which we just talked about, with finite products. So that's sort of the next thing that we need to figure out what it means. Okay, so what are finite products and why do we want them? So just a little warning, this is definitely not a definition that you'll ever see in a category theory text. I'm only using this definition I'm about to do just again because I'm taking a very pragmatic view here of trying to teach this stuff. So what I'm going to do is I'm going to start with a bunch of types. And I use the word types instead of sets because I figure as the computer science and programming background that maybe these are more familiar. So you can get the same intuition whether you think about types or sets. So I'm just going to start with a whole bunch of types, right? Subscripted by natural numbers. And they need not be distinct. So x0 might be the same as x1, right? There's no reason for it not to be. Okay, so a binary product, which we denote just with a time symbol in between these two types. So it's going to be a new type. And we can think of it as consisting of elements that are just lists of length 2, where the first term in our list comes from the type x0, and the second term in our list comes from x1. So it's not only, so the product doesn't only consist of these lists, but it also comes equipped with this function, which we call a projection map. And really what this projection map is it's a map. Sorry, I'm using a lot of different terms, arrow map function. So it's like a function that comes from your product to each factor. So K here can be 0 or 1. And what this projection map does, it just returns, you feed in a list and it just returns the kth element of that list. So for instance, if K is 1, then it'll just return, the second element in the list. If K is 0, it'll return the first element in the list. So this is, if you're learning category theory from a more traditional textbook, you'll see really the whole definition is in terms of these projection maps. These lists are just things that'll help us understand, I think, the concepts better.
So may I interject? This is Kevin.
Hey.
Instead of lists, could we call them tuples? List, at least to me, means that the elements in the list are same type. Whereas tuples, again, at least to me, right or wrong, means that the elements in that tuple potentially are different. Or they don't have to be the same.
Okay, yeah, we can use tuples. Yeah, that's fine. That's actually a word that I would consider too. I would use it often. So yeah, I'll stick with tuples, but I guess we'll just see the word lists written on the slides. Okay, so that's a binary product. Binary because we're only taking 2 types and combining them together via a product. But we can do that with the 3 types too. So we have a 3-array product where this now denoted x0 times x1 times x2. So these will contain sort of 3 tuples or length 3 lists, where again the first element in our list or our tuple comes from the first type. Second element in our list or tuple comes from the second type, and a third from the third type. And it again comes equipped with these projection maps. Where now we have 3 projection maps, one for each type. So the 0 projection map will return the first element. When K is 1, that'll return the second element, and when K is 2, that'll return the third element in the list or tuple. Now remember, just because these types x0, x1, and x2 have different notation, they may be the same. So we're just allowing for the possibility that they're different. We're not requiring that they're different. Okay, so really, all right, so this you can keep going. So you can do a 4-array product, 5-array, 6-array, and so on, to any natural number you want. All right, so you can do a billion-array product if you'd like. And then you'll have a billion of these projection maps. Okay, so there are also these sort of degenerate products. So a null-array product or a 0-array product is often, so it's like a non-tuple. It's kind of hard to describe, but we often denote it with just a sort of nondescript dot, or sometimes just by the number 1, or by an asterisk, or by an asterisk enclosed in these set brackets. And really the way to think about this is kind of like, if you remember back to pre-calculus, where if you have your variable x and you raise it to the 0 power, it's just 1. So this is analogous to that, right? So it's just like nothing times itself is just one. And a way to make sense of this is if you take a sort of recursive view of defining products as the binary product is just the unary product times another thing, and the three-ary product is just the binary product times a thing, and the four-ary product is the three-ary product times a new thing. Well, the unary product would then have to be the nullary product times a new thing. So that means the nullary product would have to be 1. So that when we times it by the new thing, we only have the new thing left. So also we have the unary product, which really is just the type itself. But I guess just to keep within the same scheme of tuples or lists, we can think of it as a tuple of length 1. But it really, you can think of it that way or just the type itself. It's either way, they're interchangeable. Okay, so there is actually a category theoretic definition of products. So here I presented them as these new types that you get from combining old types together, and these new types give you these tuples or these lists. Well, I said earlier that we're not allowed to look inside these objects of a category. So really, if we're thinking of these types as sitting inside a category, we would have no idea that these lists are in there, except that we can access them via these projection maps. Because these projection maps could be arrows, and this would allow us to sort of if you take all of the possible projection maps, which in the category theory language would be arrows, then we can take all that information and reconstruct these tuples. So while it sounds like it conflicts with this idea of we can only see things, from like a behavioral or from a macro point of view, we can reconstruct the sort of interior of these types. But again, being pragmatic and using the intuition that we have, I figured it's probably okay to think of these products as containing these tuples, at least for now and for practical purposes. So the thing is, so I started by talking about types, and we can always take the product of types or of sets if you prefer. Oops, there's a typo here. We can not always take the products of objects in the category. So can I highlight this? Oops. So right in here, there's supposed to be a cannot. So there's no reason for, just because you have a category and you have objects, there's no reason that you can certainly take their product, right? Sometimes products exist, sometimes they don't. So of types, they certainly exist, but there's many, many categories where products just simply don't exist. So they need not exist. So when a category does have a nullary product, and for any finite collection of objects, which again, you can think in the back of your mind, whenever I say objects, you can think types or sets if you prefer, because it's a nice like archetypal sort of example to hold in the back of your mind to build your intuition. But if you have this collection of objects, finite collection, and you have a product, your category does have a product of those, then the category is said to have finite products. So you need to have a nullary product and a product of any collection, any finite collection of objects in your category. Right, so that's why we have to specify in the definition of Leverrier theory that a Leverrier theory is a category with finite products, because a category need not have products. But a Leverrier theory, by definition, must have these products. Okay, so I'm about to talk about why we want them for the Leverrier theories. But are there any questions about what they are? Okay. So if not, I guess we can move on to like what do we want them in this world of Levier theories? Well, if you recall, the very first thing I said is that Levier theory is kind of the reason that Levier invented them was to place the study of algebraic structure into the world of categories. And what's one thing that's common to all algebraic structures is that they can take multiple things and turn them into a single thing. So that's an extremely vague statement, but I'm going to try to unpack it a bit. So when I say, take multiple things and turn them into a single thing, really what I'm talking about is this concept of operations. So for any natural number, there's this concept of an n-ary operation. So let's fix a type. So this is closely related to products, and you can't talk about n-ary operations without products. So we're going to fix a type. Then we have the zero or null-ary operation, which is simply a function from the null-ary product of x to x. Or remember, I would denote the null-ary product of x just by a 1. So really, this is a function from 1 to x.
Constant function, necessarily, huh?
It has to be a constant function, yeah. Because there's only one place, there's only like one thing that we're working on. So there's like no way to send two different things to two different places. So really what this is, so you can think of 1 as a type containing just a single element. And then really what this null-ary function is just picking out an element of the type x, right? So every function from 1 to x is just a fancy way of saying an element of the type x. Right? It's wherever we're sending the single element in 1 to. So again, I'm talking about functions now, but this also lifts to the language of categories where they become the more general notion of arrows. Okay, so there's a unary operation, which is just a function from x to itself, or a binary operation, which takes 2 elements of x and returns a single element of x. Right? 'Cause remember, x times x is simply a pair of elements in x. Or there's a 3-ary operation, which is a function from the threefold product of x into x. So because the threefold product is just a 3-tuple, really what we're doing is this function is taking 3 elements of x and returning a single one. And we can do this for 4-ary, 5-ary, and so on. Right. So let's consider an example. So just the integers. So the integers there are 2 famous binary operations, right? Just addition and multiplication. Right. So we can start with these 2 and make up new ones. For instance, this top bullet here is a 3-ary operation that takes a 3-tuple ABC and returns their sum. Right, so we're using a binary operation to define a 3-ary operation. And similarly, we can take a 4-ary operation, which is just z times z times z times z, returning an element in z. What this does, it takes a 4-tuple of integers, a, b, c, d, and it returns, say, the first and third elements multiplied together, and to that you add the second and fourth elements. Right, so this is an example of a 4-ary operation. So really, once you get, and this is something that happens throughout algebra, is once you have a binary operation, you can combine a binary operation with itself or possibly other binary operations to get other operations of higher arity. So, and this sort of comes automatically. You can't help it from happening. So there are also many null-ary operations with C. So for instance, a null-ary operation, remember, is really just picking out an element of Z. So for every single integer, we have a null-ary operation that picks out that particular integer. So the two most important null array operations for Z would be the one that picks out the number 0 and the one that picks out the number 1. And those are the most important because of how they interact with addition and multiplication. Oh, sorry. I don't know if you guys can hear my cat. He's a little needy sometimes. So if we were wanting to construct an algebraic gadget where we can only add and we had, then we might want to consider Z with this binary operation together with the null array operation that picks out 0. Right, and we want to combine that because that one is like the identity for addition, in that if you add by that, like nothing happens. Right. Or if instead we wanted to consider this Z with the binary operation of multiplication, we might want to pair that with the null array operation that picks out the integer 1, because 1 is sort of the identity for multiplication, because when you multiply anything by 1, nothing happens. Right, so this is sort of the power of null array operations and the way of talking about these sort of identity elements. Remember, identity with respect to a certain operation, using arrows. Functions in this case, but in the general case, arrows. So this allows us to talk about elements of a set without ever really looking inside of the object and seeing what elements live in there. We can just look at these null array operations instead. So it's, again, it's a way of like taking the micro information and lifting it to like a sort of macro view where we're not allowed to peer inside. Okay. So really, the lessons we're learning here is that algebra is really all about operations. But to talk about operations, you need finite products of your types. And so, if Levier theories want to handle algebra, which they claim to want to, then they need to handle operations, which means that they better have finite products. So that's why a Levier theory, in the definition of a Levier theory, you see the word, a category with finite products there explicitly. Okay. So we're about to move on to the next piece of the definition. So are there any questions about finite products? Anything I can clarify? Okay. So if not, we go back to the definition here and just sort of take stock of what we did. So Levier theory is a category we talked about with finite products. We talked about that. So now we have this other thing where every object is of the form m times m times m and so on for a single generating object m. So let's try to understand what the heck that means. Okay. So first of all, there's nothing special about this notation, m. It could have been anything. So when I was reading the logic as a distributive law, well, I didn't really read it, but I did skim it a bit. So Mike and Greg, they use this term m because it's evocative of the example that they used of a monoid. But really, there's nothing special about the letter m. It could be anything, right? So you could draw like a smiley face there. It really doesn't matter. So let's try to understand what an object is of the form m times m times m and so on for a single generating object means is that the only objects inside of Levier theory, so remember a category has objects. And so Levier theory is a sort of category, and so it has objects. But what we're claiming is that a Levier theory can only have certain objects. And here are what the objects are. So it contains the object 1, which is like the null array product, the object m, or denoted however you want, it doesn't matter, it's just like a black box. So the unary product, it contains m times m, which is a binary product of our chosen black box, the 3-array product of that, the 4-array product, and so on and so on and so on. So that you get an n-array product for any natural number n. So those are the only objects that our Levere theory has, right? There's nothing else. We just pick a single object, or just take a single object, we denote it however we want, and then we take all finite products of it. And then that forms the set of objects for our Levere theory. And this is the same for every Levere theory. So really, every Levere theory has the same objects. Even if they're talking about two completely different things, they all have, I'm saying have with quotes here, but they all have the same objects. Okay, so that's really all there is to it. So because it has finite products, it has all of these objects, it also contains all of these projection maps. So there's only one rule for a category in terms of what arrows they must have, and that's the identity arrows. So for every single one of these objects, there's an associated identity arrow. But there are no rules about requiring any other arrows. But because we have all these finite products, then that does force arrows into the picture, in particular these projection arrows. So what we have is a projection arrow from the binary product to the unary product. Actually, we have two, right? One that returns like one for each factor in our product. So we have three projection arrows from the three-array product to the unary product. And then we'll have, like a billion projection arrows from the billion array product to the unary product. And again, just the way that products and category theory work isn't something I want to go down a hole into, but we can actually build from these arrows more arrows. So it's sort of, these arrows in and of themselves generate additional arrows and additional arrows. So like once we throw in these arrows, new arrows just sort of appear or just sort of emerge. So that's sort of the basic thing that every Levere theory has in common is the arrows, all of these, and all of the arrows, these products and all the arrows associated with the products and that are generated by combining these arrows in certain ways. And then to actually use Levere theory to do interesting things, we would add certain arrows to, it depends on what we want to do, but we would add in additional arrows. And the arrows that we'd add in depends on our, what we're doing.
So that's how a couple different Levere theories can differ. So you said they all have sort of like these same objects and some of those necessary arrows, but then they can differ by either having or not having additional potential arrows.
Yeah, exactly. So that's where the difference between the Levere theories come into play. So for instance, when I went back way to the beginning, maybe I'll just fly back to the beginning here. And I listed all these different sort of different algebraic structures. And they're different in that they all start with a set, but then they'll have different operations involved. Different types of operations, different combinations of operations, and whatever. So it's ones we want to start considering the operations that are particular to a specific algebraic structure. That's when we'll start seeing the difference between the Levere theories associated with them.
Okay, cool, got it.
But they all have, so not all of these things have associated Levere theories. But for those that do, like semigroups, monoid groups, those are the most common ones to work with. Then they'll all have the same objects, they'll all have the same projection maps, but then they'll have different operations thrown in. So that's when they'll start to differ, only after the projection maps and the objects are already there.
Yep, got it.
Cool. So that's all I have for today. So I figure from there, I guess I kind of already talked about the first bullet. Like the natural place to go from here is talk about how every Levier theory has these projection maps, and do an actual example, like an example of a monoid, and then talk about models of Levier theories. So that's how you actually get instances of the algebraic structure, as opposed to talking about the algebraic structure itself. And then also how these things are related to monads. So I guess if we keep going in the future, these are the sort of things that I can talk about. But that's all I have for now.
Awesome. Thank you so much. And I would definitely love to keep going in the future. Yeah.
Yeah, me too. Yeah, this is great.
Great.
Yeah, I agree. That was really helpful for me.
Cool. So,
That was definitely at a good speed, but the other folks, had like questions about Levier theories before? Because I'm still sort of really foggy on the motivation.
yeah, no, I guess Greg talks about them a lot, and they are used in the ladle paper. So we're hoping to build up sort of from the Levier theories to the ladle paper. But I guess, we're not coming at it from the other direction of ladle and then understanding Levier. It might be good to hit it from that direction as well. But I haven't spent enough time with ladle, so.
Okay.
Yeah.
Yeah, that's a good point. We should understand the motivation why we'd be going down this path. What we're trying to get out of it.
Is everybody aware of Mike Stay's talk from November in the developer thing in November? Mike Stay gives a talk on from zero to ladle all the way through category theory, and the first third of it was like, oh, I can actually understand this. And then he went at like rocket speed through the rest of it. And it's like, I wanted to go back and replay that thing really slowly. But if anybody didn't know that it exists, it's definitely a piece of gold.
Okay.
We scared up.
Just a link to that.
Cool.
That sounds really awesome. I know he did ladle from the ground up in Boulder, and I, kind of like you're saying, got at the very beginning of it and then pretty quickly got lost. If there's an older one, that would be helpful too. Or is it on YouTube or anything?
It is on YouTube, and I'm finding it here. It's from November.
Okay.
Yeah, there's a good one from November. But yeah, you're right. It does kind of, after a while, you get into the weeds of some of the category theory and stuff, and it's kind of hard to follow.
I mean, when I was sitting in the room, like I said, I could follow it while he was talking for the first third, and then the rest of it, if I just play it slowly, cogitate each part, maybe I'd have a chance. But I just haven't made time to do that. Let's see. Here we go. Okay. This looks like it. So if I stick it in the Zoom group chat, is that the one?
Yeah, that'd be great. And then I'll post it along with the video, and yeah. Usually the links that are in the chat get posted along with the YouTube video on my channel. So, and then they should be posted on the GitHub, but I haven't been updating the GitHub recently with these pointers to these videos. So, Christian, I see that you're on as well, and I had the impression that you were doing more stuff with Ladle. Is there any chance that you'd be able to maybe come at things from that direction?
Sure.
Yeah,
I was going to mention that.
Okay.
I think it would, if you do a couple examples with something intuitive, like the example from the Ladle paper, it takes the theory of monoids and the theory of Boolean algebras, and you can write out phrases like A times B or C, or D times E or F. Ladle is just this nice algorithm that gives you a query language that takes symbols from both languages. And then if you can describe this nice distributive law between the monads made by these theories, it corresponds to going from a term of collections, which was that formula, and then computing it into a collection of terms, which are the results of that computation. And I think if we look at a few simple examples connecting these Levier theories that seem very abstract, but they're just trying to describe these
Oh,
languages.
1.4 million.
I think. Yeah, I think that would be good.
Okay. So I guess, you know, if our goal here is like understanding the ladle paper, do you think we should go a little bit further into, you know, some of what Daniel's objectives were in pushing forward, and then jump over? Yeah.
I think so.
Okay. So like maybe getting through the you know, particular example of like the monad as a Levier theory, that kind of stuff.
Yeah.
And then maybe hopping over. Okay.
Yeah, we don't need to get too into the nitty gritty stuff about that, but at least an overview.
Okay, cool.
Is there just a moment to remind me, Christian, what you're working on or your background or whatever?
Oh, Professor Baez and I have been contracted by Mike to basically build on the ladle paper and kind of fill in some gaps and generalize some stuff. So right now we're just working on a paper that is thinking about different enrichments for this ladle algorithm.
Okay, so it's academic research is what you're working on.
Yes, yeah.
Okay.
And Daniel, you're also a student of Baez as well, right?
Yes, I'm working on different stuff though. But
right,
yeah.
right. Cool. Awesome.
Who is that professor you guys are talking about?
John Baez.
Okay, cool.
Yeah. Great. So I guess, Daniel, thanks so much for putting the effort into this week's. Are you willing to continue and maybe take up the time next week, you know, after we have some sort of discussion on whatever Greg talks about on Monday?
I believe so, yeah. I mean, I should look at my calendar, but
okay.
I'm pretty sure that I should have no trouble putting something together for next week.
Okay. Yeah. If not, let me know. We can coordinate over email. But yeah, that'd be great. And I'm moving to Cambridge. I'll be driving out there next Thursday, Friday. So I don't know if I will be at the session or not. But if not, I think Glenn has also offered to be host there. So I'll make sure things are coordinated such that this happens next week, even if I'm not here. So, all right. Right. Yeah. Thank you guys so much. If there. And Dan, I do want to follow up with you about the link that you posted. So
cool. Moving to Cambridge. Is there any more to say on that?
Not really. I'm just moving. I'm going to continue doing what I'm doing now. But yeah.
Cambridge, Massachusetts.
Yeah. Mm-hmm.
Oh, I was just out there. Okay, because I'm out there occasionally.
Oh, nice.